Welcome back. For this model, let me bring you very close to Delft. Indeed, very close to the spot where I'm recording this video. This is where we work and where a research geothermal well will be drilled in the near future. This might be new to you, but this region plays a key role in the development of low-temperature geothermal systems in the Netherlands and probably worldwide. Any idea what all these white surfaces are? These are greenhouses, a huge number of them, where the cucumbers and tomatoes are produced, which you find in the supermarkets near you. Millions of tomatoes and cucumbers growing in these greenhouses. Because vegetables grow faster at temperatures higher than outside the greenhouse, heating is necessary. Faced with the huge heating costs, some farmers had the brilliant idea of resorting to geothermal energy. They drilled and they found warm water at a temperature of 60 to 80 degrees, which is even more than they needed for the purpose. Success was hardly coincidence. As we already mentioned, waters for heating purposes can be found everywhere, mainly dependent on the existence of an efficient aquifer. The success of the Westland farmers has generated great enthusiasm, and other farmers, hospitals and city districts are now investing in similar systems. Geologically speaking, the area we are considering belongs to the West Netherlands Basin, which is an extensional basin stretching in southwest to northeast direction from the western part of the Netherlands towards the North Sea. The basin is characterized by Jurassic rifting, followed by post-rift subsidence, interrupted by an early tertiary stage of inversion, resulting in a major unconformity visible all over the region. There are three main aquifers in the region. From shallow to deep, they are the Cretaceous sandstones, where waters have temperatures around 70 degrees. These sandstones have been drilled in a number of localities and form a proven functioning system. Jurassic sandstones are at 3 to 4 kilometers depth and should host waters at temperatures above 300 degrees. Only one attempt has been made to drill into these sandstone for geothermal properties, but the permeability was found to be too low and the well abandoned. The most challenging target is formed by late Paleozoic carbonates, which are at 5 to 6 kilometer depths and are expected to contain waters hot enough to generate electricity. The geology and engineering of these potential reservoirs are extremely challenging, but a large program has started in the Netherlands aimed at their full characterization and, hopefully, to generate energy production. The upper Cretaceous sands, called the Delftstone sandstones, form a regional, very well-known and prolific aquifer. To determine the best production strategy, the first step you need to do is to build a geologic model predicting the distribution of the aquifer in the subsurface. The pillars of these models are logs, cutting and core from boreholes. Permeable sands have been found, but how continuous are they? How big is the aquifer? Do the sands form separate lenses resulting in a small and poorly connected aquifer, or are the two sands continuous throughout the entire volume between the wells? Fortunately, this seems to be the case. Sedimentological models are used to provide answers to these questions, predicting the dimensions and the position of sand bodies. These models, with their uncertainties, are eventually used to simulate the behavior of the geothermal field. But sedimentology is not all. As we have seen in the previous clip, a dipping position of the layers facilitates flow and therefore the efficiency of the system. The map shows the depth of the top of the Delft sandstone reservoir in the chosen sector of the West Netherlands Basin. Following the deep depth lines, called isobaths, you can see that the aquifer is folded and is also affected by faults. In the seismic section, you can see these folds and faults and the position of the Delft sandstones, the aquifer of the geothermal system. And here you see the temperatures of the aquifer in key parts of the area. Differences are not very large, but large enough to keep the system running. The best strategy is to put the producer in the core of the syncline and the injector on top of the anticline. Hot water pumped to the surface by the producer is used for heating and pumped back into the aquifer through the injection well, from where it will flow along the flank of the anticline towards the producer. With the sedimentological and physical property models, we can identify the best production strategy and assess the economic feasibility of the system. What is the optimal distance between the producer and the injector wells given a certain sediment architecture? Or what is the impact of the abundance of sand bodies in the plot? You see that if producer and injector are located along a dominant sand body surrounded by shales, temperatures will decrease rapidly. If on the contrary the main channel is very wide and surrounded and connected to numerous sand bodies, then fluids will disperse and temperature will decrease much more slowly. Modeling is also key to plan the characteristics of geothermal systems which we'll develop in the future. It is better to have few systems with large spacing between producer and injector, or is it preferable to have a large number of fields, each with smaller producer-injector distances? And how will they interfere? Testing these scenarios is extremely important in areas such as the Netherlands, where a lot of doublets will be drilled. One of these doublets, future doublets, is very special to us. This is the DAP well, a well which is going to be drilled in the campus of the TU Delft. The DAP well, an exciting story of how the initiative of a small group of enthusiastic students can grow into a multi-million research facility. Like in the case we showed above, the producer will be placed in a syncline and the injector close to the top of the anticline. The DAP well will be a world-class laboratory where academic, governmental and industry organizations can test tools and workflows. And it will also produce hot water which will be used to heat up the buildings of the university. The West Netherlands Basin is and will be an exciting area for low-temperature geothermal systems because of the presence of a very productive aquifer at accessible depths and because of the large number of economic activity and settlements in need of heat. Opportunities and challenges are also foreseen in how to avoid interference between the systems. On the other side, new aquifers will be tapped in the Triassic sandstones and in the late Paleozoic carbonates. You will hear more about the West Netherlands Basin in the future.